Okay, so we have our next focus activity, but before we get to it, just a few in-house items. There are extra copies up here of the homework assignment, which is due on Monday if you needed one. If you need a copy of the focus activity, just let me know. You guys did great yesterday on your quiz. Hey, how you doing, sir? Come on in. Okay. In fact, your class average was a 91.8. That is a really good, strong start. You know, I want to keep that momentum going. I'm going to go ahead and stop early today, probably at least 5 minutes, because I want to pass back all your papers, let you start taking a look at those. But if, you know, since we're starting to take all these grades, if any of them are below 70, if they're failing, remember, you can correct anything. Now, if it's a homework assignment, you'll just go ahead and correct the problems themselves. I don't have a new homework assignment that you'll look at. So you can just put corrected on top of it, you know, turn that in and I'll take a look at it. If it is a quiz or a test though, then I have a brand new one for you to take. And I always give a week on those after they're due. So for example, we took that quiz yesterday. If you'd like to retake it to try and bring your grade up to a 70, you have until next Thursday morning by 8:05. Okay, just come on in, talk to me. We can find a time for you to do so. But the biggest thing I want to mention is next Thursday. What's that? That's going to be your test. Okay. Now, on quizzes, I don't think I'm going to go ahead and do this, but on your exams, I'm going to let you guys use your notes because I want to try to give you every advantage you can. So, you know, if you're not sure, write it down. If you have a question, let me know. I mean, I would definitely still take some time to go ahead and look over your notes because you don't want to lose time just flipping through trying to find one particular section. So you definitely want to be familiar with everything that we have. And I think I mentioned it before. If you need a binder, let me know. I can lay my hands on one pretty quick. Okay, let's take a look at it. Our second focus activity, we'll get the third and last one for the first set on Monday, and then those are going to be due on Wednesday. All you got to do is keep up with these. That is another guaranteed quiz grade. Okay, so let's see. This is what's called a compound inequality. This is what we were dealing with just the other day. Now, if you see an expression like this, x minus 4 less than 5x plus 2 less than 7x minus 3, you can solve it. Of course, you can leave it as is and solve all three parts at the same time. But for this first time, why don't we go ahead and break it up? You can create two inequalities based on the middle expression. Brandon? Oh, okay. All right. Well, let me go ahead and write it out. So x minus 4 less than 5x plus 2. And is the intersection, was that and or? Okay, I heard or, I heard and. It is and. Remember, that's everything they have in common. So then we have 5x plus 2 less than 7x minus 3. Now, solving an inequality is just like solving an equation. You want to get the variable by itself. The only thing to be careful of, what will reverse the symbol? If you multiply or divide by a negative number. Okay. Now, we can start wherever we'd like. Andrea? X, 4, 5x, or 2? What do you like?
X.
Okay. So x and 4. So you said x first. Let's start with that. So I'm going to subtract the x from both sides. But at the same time, because I'm getting the x's together, why don't we get our constants together? So I'm also going to subtract 2. So that those 2's cancel, the x's cancel. Okay. So 5x minus x will give me 4x. I got negative 6 here. Now I got to do what? Divide through by 4, and we'll have what we need. So less than or equal to, that'll be the x. So negative 6/4, negative 3/2. Okay. Now, if you're like me, I prefer to have my expression start with the variable. So I know we talked about the symbol reversing itself, but I'm going to put x here, negative 3/2 here. Okay. The symbol looks like it flipped, but it really didn't. Okay. Think of the inequality as an arrow. It's always going to point towards the smaller value. So here, in either case, the negative 3/2 is the smaller one. Okay, so I've got the first one ready to go. Okay. Now I want to do the same thing to the second one. Okay. Where should I start? Okay. So we want to go ahead and start by subtracting 2. So I'm going to move the 2 over here to the constant. So why don't we go ahead and subtract the 7x at the same time? Okay, so that those cancel, those cancel. I still have less than. The negative 3 drops. 5x minus 7x, what am I looking at? Negative 2x. Now, what's about to happen? Oh, there you go. See, I'm just saying if you're paying attention. Exactly. It's that slide teaching strategy. Years of experience. Okay, so you're absolutely right. So what's about to happen when I divide? The sign will flip. If you multiply or divide by a negative, that less than is now greater than. So this is x greater than 5/2. Okay. So this is what I want to do. I've got this set and this set. I want to take the intersection of them. Now remember, this is exactly what we did the other day. Let's create a general line graph. Okay. The two values I have are negative 3/2 and 5/2. Okay. Both are greater than, and both will have what type of circle? Open. So above negative 3/2, I'm going to put an open circle, and I would shade to the right. Those are all the values that make it true. Above 5/2, again, an open circle, shade to the right. Now, this is what I want to use to write down my answer in different forms. Remember, we wanted the graph, we wanted the interval notation, and then we wanted that solution set. Okay? But what does intersection mean? Was that the combination, or was that just what they share? Just what they share. So if we do it like this, we can see the overlap is what they share. So here's my first answer. Where am I going to start? What number? The 5/2, because that's where the overlap begins, right? So I'm going to put 5/2. I'm going to shade everything to the right of 5/2. What do you think? Open or closed? Open, because 5/2 does not belong to both sets. There you go. That is my answer to this compound inequality. Any value of x larger than 5/2 is going to make it a true statement. Okay. Now I want to write that as an interval notation. Remember, this is parentheses in your brackets. So what would I start with? Okay, so 5/2, comma what? Infinity, because it doesn't stop. And both need a parentheses. 5/2 is not included, so parentheses. If it was, we'd put a bracket there. Okay. And then remember, solution set, that's the little expression in the braces with the such that. So I'm going to say all x such that, then we have our colon. Well, since it's everything just larger than 5/2, this is typically where you'll go ahead and write with the less than greater than symbols. So I'm just going to say x has to be greater than 5/2. Okay. And you'll notice, look at all those forms. They're all telling you the same thing. Okay, we want any number bigger than 5/2. And there you go. Did anybody happen to have that ready before I walked in? No? Does it make sense? Okay, that's good. Well, okay. Let's take a look at number 2. Now, we're going to do the same thing. We're going to solve some inequalities, but what's this? That's the union, yes. So we want or. Okay, so let's take a look at our inequalities. x4, 5x, or 2. Where should I start? Negative 2. Okay, so I'm going to add the 2 to both sides. Now, if I'm going to go ahead and do that, put my constants here, let's go ahead and subtract the x as well. So those x's cancel, those 2's cancel. Negative 4 plus 2. 2 is less than 4x. 5x minus 4x. Or 5x minus 1x. And now what's left? Just divide by 4. Okay. And negative 2/4 will become what? Negative 1/2 is less than x. So again, my variable's on the right. If you like this and you work with it, perfect. Okay. How would I write it? X is greater than negative 1/2. Perfect. Okay. Or, now let's solve this one. I would subtract 2 because we already have one x term. Okay. So 5x is greater than 5, and absolutely right. Always perform the opposite operation. So now we have x is greater than what? 1. Perfect. So now exactly what we just did a few moments ago, I now want to do with these two. Okay, but the intersection was what they share, right? What's the union? Union is everything. I want to combine them into one big set. All right, so let's start with the general line graph. The two values I got from my inequalities were a -1/2 and a 1. Okay, both of them are greater than, but not included. So both will have an open circle, and both are shading to the right. Okay, so, or the union, I'm not interested in the overlap. I want everything. Okay, so where would I start my line graph? I'd start at -1/2. I want everything in both sets. So -1/2. So I know I'm going to shade everything to the right. Open or closed? Open. Okay, -1/2 is not part of that set. Now here's my question though. 1 isn't included in the other set, but it looks like he's included in my graph. Why? We're combining them, that's right. See, 1 does belong to the other one. We pulled them all together. All right. What's the interval notation? Okay, so I heard -1/2. Okay, to infinity. I know parentheses on infinity because we have an open circle. Parentheses on that one as well. There you go. Perfect. And then here's my solution set. Okay. So all x. Now, what can mean such that besides a colon? That line. Perfect. Okay. And I just want values larger than a -1/2. So x greater than -1/2. There you go. That's all there is to it. Any questions? Anybody not sure where I got something? Okay. All right, now take those two focus activities, put them together, put them someplace safe. You only need one more from Monday. You turn those in, you got a 100 quiz. Perfect, 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 perfect. Okay. All right. Well, let's see. We were talking about implicit and explicit and functions. And I don't believe we got to increasing and decreasing. Is that right? Okay. So let's go ahead and start there. And I didn't have the calculators out today. I forgot to put them out, so we'll just use my calculator at the front. And if you want one, you can absolutely grab one. But this one here, these are the notes. It says, consider the function that we have here. Moving from left to right, complete the following statements. So we're looking from where the graph falls, is constant, or rises. So from your first page with the definition, we're talking about increasing, decreasing, and constant. So you're always looking at the y values. As x is getting larger, okay, the y values, what are they doing? Okay, wherever the y's are getting larger, staying the same, or getting smaller, you use the x-axis to go ahead and describe where that's happening. Okay, so let me ask you. The first one says falls, right? So is there any place on here as you're moving from left to right, vertically the graph is dropping, the y's are getting smaller? Okay, yes, Brandon, where does it start? Oh, now we label it horizontally. Yes. So it starts at -1. So at -1, as we're moving forward, you see the y values are getting smaller. Okay, we're saying it decreases there. Okay, now it keeps decreasing until it gets to what? Until it gets to 1. See, we're looking for what the y values are doing, but we label them using the x's. So I can say that this graph falls, or think about it as having a negative slope from -1 to +1. Okay. Now, we want to do the same thing, but is there any place where the y values are not changing? They're staying the same. From what to what? Yeah. So between 1 and 5, any value of x I put in here, I'm just getting the same y value over and over again. So this is from 1 to 5. Okay. Is there any place where it's rising? From what to what? From 5 to 7. That's all you got to do. Okay. And here's what's going to make this even easier. If I wanted to go ahead and write this as an interval notation, which we're going to want, this guy here, when it says rises, that's the same as increases, right? Well, from 5 to 7, You're really going to be tempted to do this, but you don't have to. I would say it goes from 5 to 7. Okay. Now, do you see, look what's in your graph, but look how I wrote this. What's the one thing I didn't do? Like, what's the one thing you might want to do if you see this? You want to put a bracket, right? But when we're talking about increasing, decreasing, we don't care about inclusion. We just want to know from where to where is this happening. Okay. If you do put a bracket, I mean, there's nothing wrong with it. It's just that we typically don't do that. This is the one time you don't have to worry about it. Okay. So like on this guy right here, I would say he decreases from -1 to 1. Okay. Just look horizontally where the y's are going to have a positive slope, a negative slope, or a slope of 0. Okay. Now let's do the same thing here. But we want to go ahead and graph this, so I'll get my calculator up. X cubed minus 3x squared plus 2. Okay, so let's go over here. So x to the power of 3. Oh, that didn't take. Okay, I'm going to go ahead and use my mouse. It'll just be faster. Okay, so x to the power of 3, and I forgot what the function was. Minus 3x squared plus 2. Okay, so minus 3x squared plus 2. Okay, so here's my function. And we know that the guy's going to continue to go forever above and below, right? So I'm interested in just where is he increasing, where is he decreasing, or where is he flat, where is he constant? Okay. So let's see. Where is he increasing? As you go from left to right, does any part appear to have like a positive slope? Okay. So what'd you say, sir? -1 to 0. Now we're very close. It does stop at 0. You're absolutely right. But think about this. This part right here, is it absolutely vertical? Does it just go straight down? Now it does have a slight slant to it, right? So you have to think, how far left is he going to continue to push? He's going to keep going all the way to -infinity. Now, it's going to take him a long time to get out there, but he is going to continue. His domain would be all reals. It's infinitely wide. So sometimes you may not have a specific boundary. Sometimes it might be some form of infinity. So he is increasing from -infinity, but he stops increasing when he hits 0. Because, see, at that point, what's he suddenly doing? Now he's going down. The y values are getting smaller. Okay, so this is helping me out. So we're increasing from -infinity to 0. Okay. Now, he starts decreasing. The y values start dropping at 0. But where do they stop? They stop at 2. So only between 0 and 2 is he decreasing, right? So I'm going to come back over here. Decreases between 0 and 2. Now, is there anything else happening here? Oh. Is there any other place? Is he increasing or decreasing anywhere else? Where? Okay, because what happens at 2? The y values stop, and then they start to work their way up. But it's the same thing. How far right do you think he's going to go? He's going to go to infinity. Now, here's the thing. If I come back over here, there was another region, okay, where he was increasing. So what would I put between those? The union, that's exactly right. Just put a union, because those are the two intervals where he's getting larger. Okay, and it depends on your graph. Sometimes maybe your graph will only increase. Sometimes maybe it'll only decrease. This is one that did both. Let me ask you one more question. Where was it constant? Nowhere. There's no part of this graph where it's flat. Okay, so we can just put none. Okay, what do you guys think? Okay. All right. Well, let's try this one right here. We got an absolute value, and I'm going to go ahead and use my keyboard again, because that's just going to be a lot faster. So let me show you. You may or may not already be aware of where this is on your calculator. Okay, let me document B out of here. But we want absolute value, right? And, of course, I forgot to erase the board. Bear with me for a few seconds. Okay. So let's go ahead and plug this in. Excuse me. So I like to use the button right here. And again, I apologize for not having the calculators out. If you want to grab one, you are more than welcome to, or you just follow along. Right here, you see this button between 9 and the book, the open catalog? That has so much information available to you. You can do a lot of things. You'll recognize here's a fraction, here's a power, radicals, logs. These right here are piecewise functions. We're going to start those next week. What are these right here? Those are matrices. Now, the one we're interested in is absolute value. Okay, so I believe it was it x plus 2? X plus 2. Then it was a plus. Then another absolute value. Then x minus 1. And then minus 2. Okay, so there we go. So I'm just going to plug it in, and there you go. Got my graph. Okay. So now, where, if anywhere, does this graph decrease? There you go, because he's going to be infinitely wide, right? So he's coming in from negative infinity, but he stops getting smaller when he hits negative 2. Okay, so decrease, negative infinity to negative 2. Perfect. Where is he increasing? Okay, right here at 1, those y values start to climb. So from 1 to infinity. And again, you'll notice I'm not worried about brackets. For increasing, decreasing, you don't have to think about those. Is there any place where he's constant? There you go, from negative 2 to 1. There we go. Hey, how you doing, man? Come on, Warren. So from negative 2 to 1. There we go. Perfect, perfect, perfect. Okay. So any questions on increasing, decreasing? Anybody have any problems? Okay. No? Okay. Well, let me introduce you to another concept that we call relative minimum and maximum. Okay, the relative minimum and maximum values. Well, for any function f, if there exists an interval x sub 1 to x sub 2. So we're just saying that on the x-axis, there are some x values, okay, that create an interval, just like we were looking at a second ago. Okay. If an interval contains some number c, so that x is not equal to c, so c is some value between those in the interval, okay, if f of c is greater than f of x, we have what's called a local maximum or a relative maximum. A lot of times I'll use the word relative. Another teacher or textbook might use the word local, okay. If f of c is less than f of x, then you have what's called a local minimum. Okay, so let me see if I can kind of unpack this for you, because a lot of times, again, mathematical definitions are pretty often as clear as mud. So let me give you an example. Let's say we had a parabola, okay, a parabola that opens up. Now, if the graph does not go forever, okay, when we're talking about maximum and minimum, we're talking about the y value. You're always talking about the element and the range. Well, if you have a parabola that opens up, this vertex is the absolute lowest that it'll go, right? No part of the graph goes below that. So I would call that a absolute minimum. Okay. Now, what if the parabola opened down? Okay. Well, that vertex would be the highest. That would be the absolute maximum. There is nothing beyond that particular y value, right? So there is what's called absolute maximum and minimum. Okay, so why are we talking about relative maximum and minimum? Well, I'm glad you asked. Okay. Now, it doesn't show it on the graph, but pretend that the sides of the graph just go forever. Okay, so how high is this going to go? He's going to go infinitely high. How low? He's going to go infinitely low. So in a case like this, there is no absolute maximum or minimum. Because remember, infinity doesn't represent a specific number. Whatever number you say, I can always come up with a number larger, right? So what we're saying is, if the graph goes forever in one or both directions, if I just look at an interval, if on that interval, that's the highest y value we have, I can call that the relative max. Okay. It's not the largest y value you'll see in the graph, but it is the largest on that interval. That's all we're saying. The same can be said about your minimums. Okay. So if this guy right here is a relative maximum, what's this guy? He's a relative minimum. Kind of think about them as the mountaintops and the valleys. That's a good way to distinguish it. So this right here would be a relative minimum. What about this guy? He would be another relative maximum. He's not the absolute, but in his area, he can be considered a maximum, his interval. Relative max. What about this guy right here? Relative minimum. There we go. Okay. Now in calculus, when we're dealing with these polynomial functions, a lot of times it's really useful for us to know where those values occur, what value of x, and what the actual maximum or minimum value is. Okay. So let me show you this. Approximating extrema. This is going to be super easy. Okay. Right, Nathaniel? Right. All right. So we have the graph right here. It says x cubed minus 4x plus 1. So we have our function. You know, imagine that it goes forever. Okay. So what would I call this point right here? That's the relative maximum because it's like the top of a mountain, right? It's not the largest, but on an interval, he could be the largest. Now, here's the thing. He's an ordered pair, right? The y value is the maximum and minimum we're looking for. Okay, so this would be the relative max. And then we would want the x value where that occurs. Okay, same thing right here. What would this guy be? He would be the relative minimum. Again, the minimum would be the y value. Okay, so we'd have an x value where it occurs, and then the relative minimum. Okay, now there is a calculus way of finding this where you take the derivative. Oh, no, okay. Has that ever scared me? There's actually been, over the years, some female students who had startled. But no, it's never scared me. That's what happens. Yeah. Who's calling me? Here. Well, see, I'm the kind of person who see. I like to screw with people. If you haven't kind of figured out, my personality yet, I'd kind of be like, really? And then I'd probably do something inappropriate just to be like, did you enjoy? Yeah, okay. Just to screw with them. And then if they said yeah, then I'd be like, okay, maybe we need to figure out. All right. Anyways, x cubed minus 4x plus 1. And I just realized we were recording all this while we're discussing it. So yeah. So x cubed. What was it? Minus 4x plus 1? Minus 4x plus 1. Okay, so here's the function that we actually said. Oh, 4x. I'm sorry. Tap. Let me go back up here. I forgot my x. There we go. So there's the graph that we see on our paper. Okay, so we want to know what the value of this relative maximum is and what the value of this relative minimum is. So it's really easy to do. Does anybody remember doing things like this? Maybe finding the intersection on the calculator. Where do I go? Menu. Okay. Now, trace will work really well, but there is one better. If you go to analyze graph, what are two words that instantly pop out? Maximum and minimum. Now, let's go ahead and find the maximum first. So it's going to give you a vertical line, and it says lower bound, right? So you want to put that vertical line to the left of where you're trying to find that point. Okay, so we're trying to find this guy right here. So I'm going to put it, just to the left of it. And you can push enter or use your touchpad on your calculator. It's going to mark that location, and now it says what? Upper bound. As soon as I slide that vertical line to the right, it creates a shaded region, and when it hits that point, it automatically pops up what I need. Okay. So I know that the relative maximum is 4.08, and where does it happen? Negative 1.15. Okay. So 4.08, negative 1.15. Okay. So I know that's the coordinate of that point right there. And I can easily do the same thing for that relative minimum, but I'm just going to do one change. Well, it says round to 2 decimal places. I mean, the way the calculator is set, I'd be okay with this. You know, like I'm definitely going to have leeway. So if I have on my paper an answer negative 1.15, but you put negative 1.13, is it going to be wrong? Yes. I'm kidding. No, there's going to be leeway, you know, so because I know all the calculators have different settings. So as long as it's what I call in the ballpark, you're fine. Okay. Now, let's find this guy right here. So there's one change. I'm going to go to menu. I still want to analyze the graph, but he's a what? He's a minimum. Okay. So I'm looking for this point right here. So I'm going to go ahead and put him just to the left. Okay. Click enter. Slide him to the right. And there we go. So I know on that interval, whatever interval I choose, the minimum is a negative 2.08. And where did he happen to take place? It was 1.15. There we go. Now, normally how we would like to do this in calculus is by taking what's called the derivative. Has anybody ever heard of that before? Okay, maybe you have. Does anybody actually happen to know what the derivative of the function is? This guy right here? Okay, no? And that's okay. I'm not going to worry about it right now. I'm just going to kind of throw it out there. So some people have heard of it. Does anybody ever, did your Algebra 2 teachers show you this? Does this look familiar? F of x plus h minus f of x all divided by h. That looks familiar. Okay, good, because some teachers would do it, some won't. This is what's called the difference quotient, and it's the universal way for finding a derivative. Okay, basically it'll tell you the slope of a tangent line anywhere on the graph that you want. Okay, so right now I'm not going to worry about that. I was just kind of seeing if that was familiar, and that's good. That's good. We will be seeing that probably 3-4 weeks, somewhere around there. Okay, and this is our last one right here. I just want to go ahead and talk about even and odd. Now, do you guys remember implicit and explicit? What was the difference? That's exactly right. If it's solved for y, y equals, that's explicit. If it's not, then it's implicit. Okay, it's that dependent variable. Now, this one here is already solved for y, because f of x is y, correct? But these are just wanting to talk to you about even and odd. Okay, and we brought these up the other day, but let me go ahead and write down our rules. If I can take the function and replace every x with its opposite, okay, if I then simplify and get the exact same equation, it's what we call even. Okay, and it's going to have some symmetry with the y-axis. Okay, it's going to have symmetry with the y-axis. If I replace every x with a negative x, but I get the opposite of the equation, every term's sign has changed. That's what we call odd. And it's going to have symmetry with respect to the origin. Okay? So let's take a look. Okay? If it's even, you have to be able to fold it along the y-axis, and both parts come together. About the origin, imagine you just spin it. If you spin it halfway, will you get the exact same graph? Okay, so let's run through just based on what we see. Okay, here's this graph here. Just by looking at it, would you call it even, odd, or neither? Even, yeah, because this guy definitely has symmetry with the y-axis. If I fold right there, if I could fold the screen, the two parts are going to come together perfectly. So I know that's even. Okay, well, what about this guy right here? Okay, well, let's see. If I did fold it over, then are both parts going to come together perfectly? So it's not even. Okay, let's think if I spun it. Imagine just like you're spinning a fan blade. If I spun it 180 degrees, that would give me something that looks like that. But did I get the exact same graph? No, so it's not odd. So this graph is neither odd nor even. Okay, well, what do you think about this one? Definitely odd. This one here, if I were to spin it just halfway, I'm going to end up with the exact same graph. Okay, so this one's odd. So let me kind of show you what this means when it comes to doing it algebraically. Because if you have a calculator and you sketch it, I mean, you can be able to tell by looking. But if you want to do it algebraically, let's see if this one's going to be even. Okay, so let's say f of negative x equals. So all I'm going to do is replace every x with its opposite. So 4 minus x squared, oops, if I can write today, that'd be great, would be 4 minus negative x squared, right? What happens when you square a negative? It becomes positive. So this is still x squared, and you still have the 4 minus, right? So you see how even though I plugged in negative x, didn't I get the exact same thing? That's what this is saying right here. If you can plug in negative x, but it makes no difference. Okay. Now let's look at one that's odd. Okay. Let's try f of x equals, and you know what? Let's go ahead and do the one over here. That's fine. Now this one's implicit though. In order to perform the test, you have to have it as explicit. So help me solve this guy for y. So what would I do first? So I'm going to add the x. Perfect. Those cancel. 2y cubed is equal to x. Divide by 2. Those cancel. That's exactly right. Who said cube root? Okay, Genevieve. Perfect. Okay. We're going to take the cube root. That's the inverse. Okay, so those are going to cancel. So I've got y is equal to the cube root of x over 2. Or f of x, you know, however you want to do it. But now let's go ahead and replace the x with negative x. Now we said this guy was odd, right? So according to our rule, I should get the exact opposite. Okay, so f of negative x equals the cube root of negative x over 2. Well, think about it. X is just a number, right? What happens if you divide a number by 2? You still have a what? You still have a number, right? So let's say I were to give you just a real one, just kind of what if. What would the cube root of negative 8 be? What kind of 2? Negative 2. If it's an odd root, your answer is going to have the same sign as your radicand. Because think negative 2 times negative 2 times negative 2, right? All right. So it doesn't matter what number x divided by 2 becomes. This will end up being a negative value, right? Well, you see, when I solved it, I had a positive cube root, but now what do I have? If every term in the equation sign changes, that's what you call odd. Okay. How are we doing? Okay. Right. You guys are doing fantastic. All right, and I have just enough time left. I should be able to